is about to start, so if you are unmuted, and share the screen, start broadcast, and hopefully this should work now. Can you see my screen? Wonderful. Excellent. So that works. I mean, this is a little bit surprising, actually, that it works, because both of my kids are doing homeschooling and they are both in video lessons at the moment. And I'm really surprised that our internet is holding steadfast. But, you know, this is good. Touch wood. And if the person who is unmuted, could you please be so lovely and mute yourself so that the praying ears don't hear everything that you're doing? Lovely. Excellent. No, not yet. Hello. Can you mute yourself, please? No. Do you want any asynchronous material? Okay, then. Let's do asynchronous material. And can you please mute yourself? Okay. Good. Excellent. Okay, then, if you want, if you really, really want asynchronous material, then let's do some asynchronous material. But before I say something, let's give everybody a chance to join. Mm. 107 slides. Wow. Who is doing 107 slides as asynchronous? No, we do better things. Okay, let's get started. So BI301 Enzymes and Metabolism. This is the introduction. Oh, yeah. It is in the BI301 section, but let's not stress about that, right? And today it is an introduction into how I want to run this module. But before I say anything, please don't forget to record your attendance. And people have kindly agreed to post the link. So Bernardo, thank you very much for the attendance link. Now, this module is traditionally split into two parts. It's the enzymes part and the metabolism part. And they are usually around, let's say, 6 weeks for the enzymes and 6 weeks for the metabolism part, which makes it 12 weeks. And the enzymes come first. Because we need to understand enzymes if we want to understand metabolism. And in previous years, it was sort of for the last, I think, 20 years or so. Yeah, probably for the last 20 years. The first 6 weeks, the enzymes, that was my part. And the metabolism was taught by somebody else then. But since last year, I have taken over also the metabolism part, just simply because it makes sense. But I've decided to keep the slides that my colleagues produced for the metabolism part, because people always say they want slides. So, well, so here you go. This module is a 15-credit module, like most of your other modules. And we are going to have some, I think, program level multiple choice quizzes in week 15, 17, 19, 21, or something like that. I haven't looked into it. So these will be multiple choice questions. There is also an assessed practical for that. And again, I spent best part of my Christmas break in writing the program for this assessed practical, but I think it is quite good. And I don't know what this is replacing. Was just a module. I don't think you are doing BI300 this term, do you? Or BI302, or I honestly don't know. Anyway, so you have multiple choice questions and the assessed practical and another unmuted person. So this is basically the idea of how I want to run this practical. People ask me, what textbooks do you need to buy? Well, any decent biochemistry book will do. I quite like Leninger. So Leninger biochemistry, that's a really good one. There is also the, what is it called? Tumoshuk Principles of, there's another one, an online version, but any decent biochemistry textbook will absolutely do. So there's no problem. And what I have done is, because I have taught this module also previously in an online modus at a university in Malaysia, I have created a lot of YouTube tutorials that will guide you through at least the first part, the enzymes part, because that is really the toughie in terms of calculations. And so what I want you to do is for your asynchronous material for the next week, I would like you to go to this playlist on my YouTube channel. The playlist is called Enzymology. On the YouTube channel PK11 Kent. And I want you to have a look at the first 1, 2, 3, 4, 5, 6 videos that will basically cover in detail what I will just gloss over today in the session. Yes, I'm afraid there will be a lot of calculations, Serge, because, okay, I want to be absolutely honest with you. This enzyme part of the module is currently causing second-year students an enormous amount of aggro and stress. And because they are doing a project where they do hardcore enzymology, actually. And it sort of shows then who actually paid attention last year when they did the BI301 module and who didn't. Because I mean, the calculations are not terribly difficult, but you really need to practice them. So please, please, please make sure that you stay tuned in and on the ball with the calculations, that you practice them. On my practice calculation website, there is also something where you can do then the calculations when we come to them. Okay? You know that I don't very much like PowerPoint slides. So for the enzymes, the answer is no, there won't be PowerPoint slides. For the metabolism part, yes, there will be PowerPoint slides. The problem is if you haven't perfected the calculations for the last modules, I would suggest now is a very good time to get these calculations really spot on, because you will have to calculate, for example, concentrations. You have to calculate what else? Concentrations. You might have to do some pH calculations. You have to calculate molarities and things like that. And you really, really need to be on top of that, because otherwise you will get lost. So please, 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 let's get going. So in this first session, in this introduction to enzymes, I very, very briefly want to go through these 6 videos that I want you to watch then. And this is really, I want to pick out a few highlights from these videos about enzymes and what enzymes it's for next week, so you don't have to stress about it. I don't usually set very defined deadlines. I want you to know when you have at least finished the course that and how enzymes are, for example, how they react to changes in pH or in temperature or something like that. So I will specify any deadlines when I really mean it, but if the deadline is sort of, it is for your understanding, then you know, you can do it whenever you want it. So don't stress about it. Life is too short to stress. Right, now, what are enzymes? Well, enzymes, and another thing that I really, before I get started, I need to declare here, one of the problems is you all have done enzymes in your secondary school, haven't you? All of you have done enzymes for A level, at least. Yeah. And you see, that is exactly the problem that I have, apart from unmuted people. Because the way it is taught at secondary school is, well, there are lots of lies in it. Or enzymes do exist. But for example, when we come to inhibitors, you will find that the way you have been taught at A level is just simply pretty shite. You will also discover that quite a lot of biochemistry textbooks don't get it right. So stay tuned for these things. Okay, so what are enzymes? And why do we need them? Why do we bother? Oh no, they can look like Pac-Man. Jeremy Pac-Man. So what are enzymes? Okay, they help with a reaction. What are they? They are proteins, okay? They are biological catalysts and they are proteins. One statement is definitely true. The other one is mainly true because, yes, they are catalysts. And we discuss that in a minute, what a catalyst does. Do they have to be proteins? The answer is no. Not all enzymes are actually proteins because in, I think, 1980 or something like that, or 1970, it was found that also RNA can be an enzyme. So RNA can have catalytic function. Special RNAs. And in a way, if you think about it, this was a massive, massive break with the paradigm. Enzymes can only be proteins. And I think the guy got the Nobel Prize. Thomas Cech got the Nobel Prize for that. So certain RNA molecules can have enzymatic function. So what is a catalytic function can act as enzyme. So what is a catalytic function? Well, the definition of catalysis is basically a catalyst takes part in a reaction but is not consumed in the reaction. So if we, for example, say we have a substrate and this substrate is converted into a product, and I indicate it like that, then a catalyst, there's an S missing, a catalyst will do this, will participate in the reaction, but it will not be consumed. And absolutely right, you can use this example. A fork is a catalyst for meals, or a knife is also a catalyst for meals. And the way we can write it is substrate. So that's the substrate. That is the reactant in this reaction, plus the enzyme or the catalyst. And we can write it sort of as an equilibrium, gives us the product plus the enzyme. And this enzyme then can start another cycle immediately afterwards. It doesn't need to do anything. And we can have the same enzyme participating in many, many, many of these catalytic cycles. And what's going on in between here, for the moment, we just simply leave that as sort of almost a black box. Now, when people say it reduces the activation energy, and a catalyst in general, this is absolutely true, because what an enzyme will do, or catalyst in general, catalyst will reduce the activation energy of a reaction. However, and there is something that a catalyst cannot do. Does anyone know what a catalyst cannot do? Exactly. Charlotte, you're absolutely right. It cannot affect the equilibrium. Now, let's have a quick look how an energy diagram for that would look like. So here we have a sort of a makeshift energy diagram. Here we have sort of a reaction line or reaction timeline. Oh yes, is that football? And here we have the free energy, also referred to as sometimes Gibbs free energy. We have our substrate be located here, so that's the substrate. And here we have our product, and that's the famous sort of diagram for that. Now, the equilibrium state between the substrate and the product is given by this energy difference, by this. I probably should, it's a little bit too long, is given by this difference here in energy. So that is delta G. That's the Gibbs free energy. And this determines the equilibrium. So this part here determines the equilibrium of a reaction. And we will discuss that in more detail when we get to metabolism, because we will find some really interesting things there. Now, very often we find that the substrate is not immediately converted into a product because there is a sort of an energy barrier between the substrate and the product. So the substrate is just sitting there here, and it cannot move to the product side because there is this huge mountain in between. And this here is the activation energy. So activation energy. And very often it is abbreviated as E-act or something like that. This is how for most reactions, this is the state of the play. Now, with a catalyst, and it does not necessarily have to be a biotic catalyst, an enzyme, it can be also an abiotic catalyst, but any catalyst, what they do is they reduce this activation energy and make it easier for the substrate to get over this hill. So they reduce this activation energy, and that is with a catalyst. Not necessarily an enzyme. It can be an inorganic catalyst as well. You have experienced one of those inorganic catalysts when you did the sugar, when you discussed sugars, couldn't you? How do you get from a sugar to the corresponding acid? So from glucose to gluconate. Now that you have done that, because you had a reducing sugar, and this sugar was converted into an acid, what did you need to use for that? No, can't remember. Copper ions. You used copper ions. There was no oxidase or anything like that. You used copper ions in the Nelson's reagent when you did the honey practical, I think. And copper was a typical catalyst that just simply reduced the activation energy. Now, the big question is, what happens to this one here, to this delta G, in the presence or absence of a catalyst? Does it change this difference? Does this difference, this delta G, change? It always stays the same. And as I said, this delta G, that determines the equilibrium. So without a catalyst or enzyme, we have this massive mountain here, but delta G stays the same. With the catalyst or the enzyme, we've got the pink line here. So the activation energy changes, but delta G still stays the same. So a catalyst or an enzyme never changes the equilibrium. Of a reaction, at least of a simple reaction. There are ways where we apparently see a change in equilibrium, and I will discuss that with you when we come to more complex reactions. So it looks like the enzyme changes the an equilibrium, but what it actually does is it sort of directs the product onto a different pathway. Metal ions very often have catalytic activities. And in the case of the glucose, you had the glucose molecule where you've got the aldehyde. And in the presence of oxygen and copper ions, you convert this into actually something like that, where the glucose, the aldehyde, turns into an acid. And this would usually not happen just in the presence of oxygen, but if you've got copper ion, like Nelson's reagent or Tollen's reagent, I think Tollen's is with silver, but copper ions act as catalysts for this reaction. And I think that is a reaction that you did in one of the practicals. So catalysts, they reduce the activation energy. And I heard some people earlier discussing the Arrhenius equation. Yeah, absolutely. You can write the Arrhenius equation. This was the rate constant of a reaction equals an steric factor times E to the power of minus the activation energy divided by RT. So here the A is usually abbreviated for steric factor or a scaling factor. R is the what is called the Rydberg constant. The activation energy, that is EA, so that's the activation energy. And this is the temperature in Kelvin. And that is the rate constant. And you probably have seen some Arrhenius plots and things like that, where you can make where you can transform that into a linear relationship. I don't want to spend any time on that because we are not really dealing a lot with these rate constants in this context. We will deal with rate constants then on, I think, on Friday when we look at the relevant equation. Okay, so enzymes cannot change the equilibrium, but they change the activation state. And because we have enzymes, because they are usually proteins with some exceptions of the RNA molecules that have enzymatic function, we know proteins are sensitive to temperature. And what else? What else are proteins sensitive to? Absolutely. Temperature, pH. Some proteins are actually sensitive to pressure. Some proteins are also sensitive to lots of what we call effectors. And this will be a major part of this module, especially in the second part, and when we look at metabolism. Now let's look at the temperature sensitivity of enzymes. So temperature sensitivity of enzymes. And you probably, yeah, you are right, salt concentrations, these are all these effectors that can have an impact on an enzyme. You probably have seen, this is not straight, you have seen these diagrams where you plot the temperature, let's say in degrees centigrade, and the activity of an enzyme. And we will discuss probably on Friday what we mean by activity. But for the time being, let's just simply say how active the enzyme is, whatever this means. And an ordinary protein will have a profile like that. So that is a typical temperature profile of an enzyme. And what we see here is that when the temperature is too low, so in this range, the enzyme is not going to be fully active, just simply because it cannot do at these temperatures, it cannot reduce the activation energy. And as we know, the activation energy also depends here on the temperature. So if the temperature is not right, then the enzyme, with the best will in the world, can't do a lot in order to reduce the activation energy. When it gets warmer, the enzyme, the reaction increases. And then it comes to a point in this region here where, as a protein, what do you think happens in this region here where we see a slowing down and then this rapid drop? What happens in this case? What happens? Absolutely right. The enzyme denatures. So denaturing means the temperature gets too hot and the enzyme will unfold. Enzyme unfolds. And when the enzyme as a protein unfolds, then it does no longer have the correct three-dimensional structure to do what it is supposed to do. Is it possible to have two optimum temperatures for an enzyme? You can, I suppose it is possible that you can have two optimum temperatures for an enzyme if the enzyme has modification. So if the enzyme, for example, has a particular modification at one point, then it has one optimum temperature. If the enzyme has another modification, then it might have a different temperature optimum. So it can happen that an enzyme can have different temperature optimums. Not unheard of. Now, obviously, when we talk about enzymes, enzymes are the building blocks of life. So when we look at different organisms, these organisms can actually survive under different temperature conditions. This also means that these organisms must have adapted all of their enzymes to be functional under these environmental conditions. Does that make sense? So, for example, for humans, our conditions inside the body is 37 degrees centigrade. So all our enzymes in the body, and I mean all enzymes work well at 37 degrees. If we had an enzyme that would not work at 37 degrees, then obviously the organism, us, would not be able to survive. Makes sense, doesn't it? Obviously, there are organisms that don't live at 37 degrees. And therefore, they must have adapted all of their enzymes to work under the conditions where these organisms live. So, for example, we might have psychrophilic organisms. Let me write this properly. So we have psychrophilic organisms. What are psychrophilic organisms? Pretty crazy, yes. They're not psychophilic, psychrophilic. Nope. They are exactly the opposite. That's right. They are also called cryophilic. These are organisms that are adapted to live in low temperatures. So low temperature organisms. And they can, for example, they are quite happy at temperatures below 0 degrees centigrade. Or, in other words, their enzymes are all adapted so that they work very well at sub-zero temperatures. If you put a psychrophilic organism into, at room temperature, what we define at room temperature, they would probably die because all or some of the enzymes will show this denaturation curve. So these are psychrophilic organisms. What is the opposite of psychophilic? The cold-loving. What is the opposite to cold-loving? No, they are the thermophilics, exactly. So thermophilic. These are organisms that like it hot. They are the hot-loving organisms. And we, in general, distinguish 3 classes of thermophilic. Not the pyromaniacs, but some of them actually have the name pyro in it. Tardigrades are actually a very interesting organisms because it seems these are one of the very few multicellular organisms that can survive high temperatures. And with thermophilic, this is usually temperatures between, say, 50 to 70 degrees. So these are organisms that can not only survive temperatures of 50 degrees to 70 degrees, they actually thrive in these temperatures. They can multiply. For them, room temperature is, say, 65 degrees. And it means that all of their enzymes, not just some of them, all of their enzymes have to be adapted to work very well under these conditions, in these high temperatures. There are then what is called the extremophiles. And these are organisms that live at temperatures between 70 to 90 degrees, roughly. There is a sort of, just to give you an idea of the range. These are organisms that survive not only but thrive in conditions of 90 degrees. Does anyone know where the world record stands for living and also reproducing? Where is the world record? 96? Nah, that's too cold. That's a little bit too high. Archaea would not withstand 1,000 degrees. You are far too high. They are called the hyperthermophils. And the record is the strain of, I think it's called Methanopyrus candleri, strain 121, because at 121 degrees centigrade, this strain is still able to duplicate within 24 hours. And where do you find these strains? Because obviously 121 degrees, water is boiling, water is no longer present, water is evaporated. But what you will find, where you find them, is in exactly hydrothermal vents. These are at the bottom of the ocean. Pressure is extremely high. And these are sort of volcanic vents at the bottom of the ocean, high pressure, extremely high temperature. And that is where you find these hypothermophils. Have you actually ever worked with an enzyme from some of these really weird organisms? Absolutely right. Yes, you have. You have, because you've done PCR. Remember PCR reaction? In PCR, in a polymerase chain reaction, the enzyme that you use comes actually from an organism called Thermoaquaticus or Thermophilus aquaticus. And the enzyme is usually called TAC. This is a DNA polymerase of this particular thermophilic organism, which has its pH, which has its temperature optimum around 72 degrees centigrade. So you have experienced a thermophilic organism. Also, if you use biological washing powder, it's not because it is particularly good for the environment. That's not why it's called biological washing powder. It is called biological washing powder because it contains enzymes, and many of these enzymes are from thermophilic organisms, so that in the wash, the enzymes get released from the washing powder and can do what they are supposed to do. So they break down proteins and DNA and RNA molecules and fat molecules and lipids and so on and so forth. That's in your clothes. And in order to do the wash at a higher temperature, you need these enzymes from thermophilic organisms. So biological washing powder, you usually should not use it at a very, very hot wash because most of the washing powder then just simply dies. But you can easily use the biological washing powder at 60 degrees because the enzymes in the biological washing powder are from thermophilic organisms. Same if you use a dishwasher. The dishwasher tablets actually contain enzymes from thermophilic organisms. Well, some people have allergic reactions to the enzymes because if the enzymes are not washed out properly and they are still sitting on your skin in the wash, they might do horrible things then. And some people react with rashes and allergic reactions to these thermophilic enzymes. Absolutely right. But what this also shows is that we probably need to rethink our definition of life. When we are looking at life outside this planet in a way. So if you are thinking about life on other planets, we have this sort of conception of life can only exist in, a very small temperature range, let's say from 10 degrees to say 40 degrees centigrade. That is where we would be, comfortable surviving. But with these organisms that have adapted to life under extreme conditions, we probably need to rethink this. Where could we find life? And there is actually no theoretical limit why, for example, the survival should stop at 120 or 130 degrees. As long as it does not interfere with breaking bonds, covalent bonds, I would not be surprised if life could potentially survive up to 150 degrees. So when we are looking at life outside Earth, we probably need to bear that in mind, that what is really a nice temperature for us, for other organisms, it might be way too hot or way too cold. Hypothermophiles will not survive at temperatures below, let's say, 50 degrees. Absolutely not. If you have an enzyme that is a thermophile enzyme, this whole curve here that I drawn here will be, well, it might start here at, say, 60 degrees, and it will stop at, say, 140 degrees centigrade. for example. And a characteristic of the hyperthermophiles is that they do not survive temperatures below 50 degrees. Many cyclophilic organisms will just simply not survive temperatures higher than 0 degrees. Absolutely right. So, something for you to think about. What I want you to do is also have a look at the pH dependency of enzymes, because we will find again that enzymes require a certain pH in order to be active. If you are outside this pH, the enzyme will not be active and therefore will not work. So we also then have organisms that are that survive under extreme conditions, very low or very high pH. And as I said, what I want you to do is for, next week, I want you to watch these 6 videos that I've got here, the first 6 videos, enzymes past and future, up to the temperature dependency of enzymes. And you're absolutely right. There might be life, but not exactly how we would recognize it, but maybe the same. We might be able to recognize it. So I think this is really fascinating. However, my time is up. So thank you very much for watching. And we will continue with the enzymes on Friday, where we will introduce one of the most important equations in enzymology, the Michaelis-Menten equation. So thank you very much and see you soon. Have a lovely day. Take care. Bye-bye.